Were you happy with the outcome? Were you happy with the outcome?
Well, I haven't seen everything yet.
Okay.
I've seen some of it, but not all of it. So it's a lot of surprises for me too, I'm sure.
I did a tweet last night, Stephen. I just got into this Twitter thing fairly recently. But I did a tweet for this and these projects. So I promise I only got 6 followers. Hey, how you doing? Good, how are you? I'm just telling Stephen I got a Twitter account opened and I did a tweet last night. Thank you for this event. I found this, I only have 6 followers. Maybe it'll grow.
Yeah.
Thank you. So we've got this.
All right, I'd like to next introduce Team 2. This team is sponsored in part by Marathon Oil, who gave us some funds to do a project for the Resource Center for Persons with Disabilities, RCPD. And Steve Blosser, who is here, is the facilitator, or the sponsor, rather the sponsor representative. Dr. Deller's the facilitator. And Team 2 is going to talk about an indoor digital orientation communication enabling navigational technology, or what's called iDocent.
Hello everyone. Thank you for taking time to come to our presentation. We are EC4A Design Team 2. My name is Kurt Katana. This is Vadim Kim and Adam Partlow. And today we're going to talk about the project that we've spent many long hours working on in the 480 lab called iDocent, Phase 2. And really what iDocent is to solve a problem. And the problem is indoor navigation. Currently we have GPS capabilities and technologies available, TomToms, Garmin's, even smartphones. They're able to navigate outside using the GPS satellites. But once you get inside a building, due to the metal in the building and other interferences, those capabilities are greatly reduced, almost to nothing. And the purpose of our project was to find a solution for that. Our target user are the visually impaired. I've been working with the MSU Resource Center, persons with disabilities. But also our product is hoping to potentially expand to work for everyone. Little background. As you notice, this is Phase 2, as I mentioned, and it's a continuation from Phase 1. Phase 1 used a smartphone interface, a smartphone application, and they used Wi-Fi triangulation to locate where they are by use of hotspots located within a building, existing Wi-Fi hotspots. And from there, they would triangulate where they were in the building. We decided to take a new approach to this, and we decided to use audio signals to be able to locate somebody. Similar to Phase 1, we're also going to use a smartphone application to be able to do this, but the sound signal, to be able to locate, the sound signal would be the speaker on the smartphone would emit a sound signal, and from there be able to locate where the person is. The sound signal would be picked up by microphone modules that would be located around a building. Some of the objectives that we came up with in the beginning of our project, first of all, to use a smartphone as the primary device to be able to navigate. One of the advantages of this is that most people, well, eventually, most people will have a smartphone because it's an emerging technology that will be coming down in price. So no additional hardware will be required. Well, that was my third goal, getting ahead of myself. Second goal was to locate the person, their accurate position within 10 feet. Third, as I mentioned, no additional hardware for the user. And fourth, to provide audio feedback for the visually impaired. Now, here's Vadim, and he's going to talk about how we achieved these objectives.
To reach some of these objectives, we, at the beginning of the semester, we kind of established a guideline to help us get everything set up and meet all the requirements for this project. And our first step was to develop a smartphone application, which would emit a audio signal, targeted audio signal, and which would not require any additional hardware, any kind of speakers, any buttons outside of the smartphone. Second step was to select the hardware, which is pretty much to make up the microphone module, which would use a microphone to receive the audio signal from the smartphone speakers, and also a bandpass filter, which would attenuate all the noises and would only receive the signal from the smartphone. Amplifier was used to amplify the noise, the signal from the microphone, and make sure the ADC converter would pick it up. And of course, power supply to keep the whole microphone module running. Third step was to test the module, to make sure it picks up the audio signal, and we receive some kind of data at the server side. And then once that is established, it was just a matter of programming and putting everything on the cell phone and setting up the whole system, and make sure multiple modules are connected to the server and are able to communicate to each other and output user's location. Here's a flow chart for the user to follow. First, iDOSM will be available just like any application on the smartphone, most likely to be free, where all the maps and for the buildings would be available. For example, for MSU campus, all the maps would be available on the website. So the user would download iDOSM, then the user would open the program and press the Locate Me button. The Locate Me button would output audio signal, as I mentioned, through the cell phone speakers. And these signals would be received by microphone modules in the area, and microphone modules which would be connected through the Ethernet, they would send a notification to the server, which would put a timestamp on every signal. And then the server will use the first 3 timestamps to triangulate a user's location and send the final location to the user. And here's the basic setup. As you can see, this is the 3rd floor, for example, of the Union building where we currently are. And for example, if the user would come in and he or she would be lost, he would pretty much just open the application, press the button, which would be received by all the closest microphones in the area. And all these microphones are directly connected through Ethernet, as I mentioned, to the server, and then the server would automatically send the user's location. And here's Adam to talk a little bit about software and hardware.
My name is Adam Harlow, and I'm going to go over the system protocol and some of the components. The first thing we have here is we have the smartphone over here on the left. We have the microphone here, microphone modules represented here in the center, and the server here on the right. So the first step that this would do is the smartphone is going to contact the server to make sure that it's available to send the audio signal. The server is going to let the smartphone know that it's online, and then the smartphone will then emit the audio signal to all surrounding microphone modules in the area. Each of the microphones will then send that notification over to the server, letting them know that they received that sound. Then the server will then analyze that data and send that back over to the smartphone and with the location. And then you're wondering, how does it calculate this position? Well, it uses the first 2 timestamps for that calculation, takes the position of the microphone modules that is known, and if 2 are not given, then it only takes 1 into account. And then using that difference in timestamps, known speed of sound, and the position of the user relative to each module, then that location can be calculated. And then Kirk's going to go over system design.
So using this current configuration for system design, some of the advantages is that it minimizes transmission delay. Since no timestamp is collected from the phone, all the timestamps are assigned on the server. We don't have that delay in between transferring between the cell phone and the server. Also, since all the microphones are connected hardwired through Ethernet on the same network, delay is pretty negligible, very small, and not really to take into account, or it wouldn't really make much of a difference. Yeah, as I mentioned, timestamps are on the server side. Also, this ensures clock synchronization across all the devices. And the process continually repeats. So instead of the user just being found in one location, it just continually repeats, and they are navigated to where they need to go. May it be a classroom, bathroom, food court. Some of the system components. iDosing contains 3 main system components. First off, the smartphone, the actual smartphone device, and also the application that will be run on the smartphone. Second, the server, to be able to collect all the signals and calculate the time delay. And third, the microphone modules that will send the sound notification to the server.
Our main platform, we use Samsung Focus, which was donated to us by Microsoft. And the main advantage of this is it runs on C# and it's really easy to program and run any kind of like simulations and visual kind of programs, buttons. Just pretty much, it was really easy for us to program for navigation purposes. And this is how the actual program looks, and this is iDosing application, and here's a locate me button, and it would automatically download all the maps from the server, all the available maps from the server, and once the locate me button pressed, it would automatically emit the audio signal and just wait for response from the server with location information. Yeah, to add.
Alright, so the server that we used, is programmed also in C#, and that is actually a local server connected by Ethernet via the router, and that just monitors all the TCP IP ports and for all the incoming communications from the smartphone and the microphone modules. And then our next component is the microphone module, which consists of 4 main parts. We have the microcontroller, the electric condenser microphone, the Butterworth bandpass filter, and the power supply to power the whole module. So the microcontroller that we decided to use was the Arduino Plus, which is Ethernet enabled, has an analog to digital converter, and also, like the server, is also programmed in C# and the .NET framework. So take a look inside our microphone module. First we have the power board, which has incoming of plus and minus 15 volts, plus 5 volts, and outputs along with those 3 voltages. The 12 volts coming through our LM340 voltage regulator. And then when the sound comes in, it comes in through the microphone, which is pointed out towards the back of this box. That audio signal comes in and goes to our main microphone module board, into this port right there. Now that signal is going to propagate through our bandpass filter, which is a 5th order Butterworth filter. And for the bandpass filter, we decided, after consideration of all the other op amps for the LF411, due to the JFET construction, and which gives it a high input impedance and low noise. So from that bandpass filter, we need to pick up this low voltage signal that's coming in. So we have our amplification stage down here, and for that we end up using the OPA 134, which is a very low noise op amp. And in order to adjust our gain stage, we have a 10-turn 100K ohm potentiometer down here, so we can adjust the gain and the sensitivity of the module itself from the outside of the box. And then that output will go to these terminal blocks, which also supplies the power to the board. And that output goes over to the microcontroller adapter board here. And also powers the board here. And an Arduino is located underneath that adapter board. And then the signal is sent out through the Ethernet port located right there. Taking a look outside of our microphone module, we have the gain adjustment. As noted earlier, we have the microphone and the power input. And then we also have the Arduino USB and Ethernet. The USB is for programming, the microcontroller. And then Vadim will take this one.
Here's a quick video demonstration of how this whole system runs. So here's a user which would open its focused cell phone, and they would open iDosen right there on the bottom. So it was made in the hallway. As you can see, there are microphone modules. I'm not even going to try to click on the screen anymore, but there are microphone modules laid out on the floor right there. And then the user will press locate me button. So the audio signal is outputted. So as you can see, it puts on the mark where the user is located. Next signal is outputted. As you can see, those microphone modules receive the audio signal again, and they calculate location. For this video, we just pretty much inputted our wanted location, and see we put our microphones in between the two doors. That's how we had the whole system set up, and see how accurate it was, and we were able to establish 10 feet accuracy. At the beginning of our semester, we were given $500 as our budget, and we were able to fall within that. And our major components, a major chunk of money was spent on our Arduino microcontrollers, which we bought 3 of those, and we saved a lot on the cell phone, which was donated to us. We didn't have to buy one. So we were able to save a lot of money, and ended up saving $102. As a result, we were able to accomplish all the objectives that were established in the beginning of the semester, which was to create a smartphone application, success, and then we were able to fall in within 10 feet accuracy, which we run the video last night around 3 o'clock in the morning, but we were pretty accurate with all the readings and multiple tryouts. So, and we were able to do all of this with no additional hardware to the user, which was one of our main objectives. And due to time constraints, we were mainly focused on making hardware for the system, and we left audio feedback to future development, which is hopefully for next year.
In working on this project, many long nights were spent scratching our head trying to figure out how we were going to implement this. But in that process, we came up with some future recommendations for whoever, if anyone would like to pick up the project in the future. First off, the sound frequency. The frequency signal that we chose happened to fall within human hearing range, which can be an annoyance, to say the least, for the user and also for nearby people. So in the future, a sound frequency should be chosen outside of human hearing range. Also, in developing this prototype, we only counted for 1 user. If this is going to be in the public domain, it needs to be able to handle multiple users at the same time, simultaneously. We didn't really get the chance to really indulge with any security that the system would have, so it's very vulnerable to mischievous attacks that could occur. For our smartphone application, we use the Windows Phone, but for it to be able to be user-friendly for everyone, we need to also look into development on multi-platforms, such as Android and iPhones and other OSs that may come out for smartphones. The microphone module box, this is it right here. It's kind of bulky. In the future, this could be redesigned to be a lot smaller. And also the cost, as Vadim was just mentioning with the budget. The Nadrino Plus contains a lot of additional features and a lot of additional usability that we had not used. So maybe being designed for a microprocessor that would be specifically for this application would save on the cost. So, in conclusion, we concluded that audio signals can be used for indoor navigation. Smartphones can be used as the primary device to locate. It's very easy to use and also to implement into buildings. One of the advantages that I don't think we mentioned were that microphone modules are exclusively used for location, for iDocent, as opposed to phase 1, where using Wi-Fi, everyone's open to using their Wi-Fi, so it's not a dedicated system. And our product has great potential in the public domain, possibly to be implemented in museums, hotels, airports, and other large public areas. Thank you for your time. Any questions?
Thank you. Some questions for the group? Mike?
Sounds like your time coding was done on the server and not on the microphone boxes. What's the implication of that?
Initially, it was for time delay, because
Well, we did our programming on Arduino, but to eliminate the time delay with the connection from the smartphone to the microphone module, we wanted to eliminate it before there would be no error.
Yeah.
So therefore, we just decided to do all the calculation, timestamping on the server, rather than sending a timestamp signal to the module, which would then send it to the server.
I guess my thought was you're introducing delays, aren't you, in the Ethernet network then that confound your study, right?
Correct, but due to the speed of sound being at kind of a slow rate, the propagation delays become fairly negligible.
Okay.
Have you guys actually quantified that at all? What those delays might be? Have you quantified those?
we haven't gotten that far in our testing to really have a definite conclusion.
Yeah, this video was made like 3 o'clock in the morning last time. We actually finally got our project running and actually working this time, so yeah.
Tight time constraints.
It is possible, of course, to do the time stamping on the microphone receiver, because there's a real-time clock in the
Right.
unit, so you could do that.
It is a possibility, but in our discussions and for our design, we chose to do it on the server side.
Okay.
But that is an option. That is a route that we considered and we could have gone down.
How much, do you have a feel for how directional the microphones were that you bought?
The microphones are actually supposedly omnidirectional, but we're thinking the smartphone is actually not as omnidirectional as the speaker on the smartphone is not as omnidirectional, and there really is no omnidirectional transducer. They claim that, but you come up with a weaker signal when you come in on an angle as opposed to direct on.
So do you think that may have been a contributor to your uncertainty position?
Yes, definitely.
One last question, since you never described your Butterworth filter in terms of the actual transmission characteristics, but did you think at all about using with the individual in motion, whether you could use micro-Doppler to resolve ambiguities?
I'm actually not familiar with micro-Doppler.
Well, I mean, you're walking, right? It's the train whistle at speed, right? So there's a slight difference if you're approaching the microphone and then walking away. just wondered whether you thought about whether or not that might be used to distinguish between various microphones. And I'm walking away from this one, but I'm walking towards this one.
Well, we definitely thought about walking away from the other microphone, because that way, that one's really only getting an echo as opposed to the actual full sound that's coming. So there would be some delay there. And
We mainly chose Butterworth because our group members are in one of the classes, and we became really familiar with Butterworth's filter design, and it was due to its bandpass, it was pretty much perfect for our setup. But as you mentioned, other filters could be also implemented in this design.
Seemed as though the tone you used was probably a second or a second and a half long. Why that long of a tone? Did you need that much time? Do you monitor the start and the end phase, or?
We pretty much, no, what we did is our modules, we only had two set up, and our modules would receive the signal, and they would, for the purpose of showing that the system could work, we took the average of every data that was recepted, and we pretty much, it was pretty accurate. It was within 12 feet, I believe, with accuracy. And because we started with a higher frequency, but because currently speakers on the smartphones are not able to output, we were starting at 20 kilohertz, but we weren't able to output with enough amplitude.
I meant mostly the duration of the sound seemed a little long. Like, did it need? You were measuring just the onset of the sound when it arrived, or were you monitoring when the sound ceased also on the server side?
we're actually taking the average of the times.
Okay.
So the microphone modules would receive those two timestamps, but then they would also receive it again and then take the average of those distances.
So that was a calibrated length of a tone then?
Yes.
Yes.
Okay, I got that.
Question. I was going to ask, you mentioned echo earlier. Did that ever cause any problems with this measurement?
That's actually the reason why we started taking the averages and calculating the location.
Okay.
Because we started not having defined lengths of time that the sound signal would be sent out, and we were getting sporadic results. By taking the average and having a calculated time that the sound signal was sent out, we were able to have more accurate results. I think we had about a 70% success rate, as opposed to, I think it was 20% before we were doing that.
Okay, we gotta,
Was that frequency you selected within the human voice range at all, or did you have any confounding
The
variables?
human voice range, I believe, is between 60 hertz and 5 kilohertz.
Okay.
And the frequency we chose was 1.05 kilohertz. So it
You had
was.
to be
and
quiet. Yeah.
There was, yes, there was.
And it wasn't a controlled environment from 3 a.m. No one was around. So.
Okay.
Besides the other design groups.
all right, thank you, sir.
I know my mother. My mom doesn't have a computer, so I'm going to give